Welcome to Brain Vision.
So for part A, we want to set this up. So we have RU, which is the partial derivative of R with respect to U, and that's going to be, we'll write it as a vector. So it's going to be A cosine V, B sine V, 2U, and then RV is going to be the derivative of R with respect to V, and that is negative AU sine V, BU cosine V, and 0. Then we want to take RU cross RV. When we do that, we get negative 2BU squared cosine V negative 2U squared A sine V and ABU. So with all that being said, we see that its magnitude, what we'll end up getting, we're going to want to use its magnitude. So A of S will be the double integral of the magnitude dA, and that's going to equal the second derivative, or the double derivative. In this case, since we know U is from 0 to 2 and V is from 0 to 2 pi, what we'll end up having is this right here, which will be 4b squared U squared cosine squared V plus 4a squared U squared sine squared V plus a squared B squared dV du. And with that, we see that this is our final answer for part A. Then for part B, we want to eliminate the parameters to show the surface is an elliptical paraboloid and set up a double integral for the surface area. So we have our three equations: x equals AU cosine V, y equals BU sine V, and z equals U squared. And then what we're going to do is divide both sides of the equation for equation 1. So we'll get U cosine V is equal to x over A. And then if we square both sides, we get that x over A squared equals U squared cosine squared V. Then doing the same method, we get that y over B squared equals U squared sine squared V. So with all this in mind, we add those together. If we add these, then we get that x over A squared plus y over B squared is going to equal this plus this, which cosine squared plus sine squared is just going to be 1. So it's just going to equal U squared, which is just Z. So based on that, we see that this is the equation of an ellipse, and the paraboloid will be above the z-axis since z is always going to be positive. So we know that this is the equation of an elliptic paraboloid with the z-axis of symmetry. To find its surface area, we'll do this. It'll be equal to the double integral of the square root of 1 plus dx, or dz dx squared plus dz dy squared dA. And then using what we know about them already, we see that dz dx will be (2x over a squared), dz dy equals 2y over a squared. So what we'll ultimately end up getting is this right here. We can just replace this right here with the value squared, so it'll be a 2x over a squared and a 2y over a squared. So that's what we'll get. And then based on this, we can ultimately convert it into another form if we want to. We're able to convert it into polar coordinates. However, we can just leave it as this for now. If we wanted to convert it to polar though, what we'd end up getting is AB from 0 to 2 pi, 0 to 2, r times the square root of 1 plus 4r squared cosine squared theta over a squared plus 4r squared sine squared theta over b squared, and that's dr d theta. But this is sufficient as well. This is just what it takes to convert it to this. Then for part C, what we're asked to do is use the parametric equations with a equals 2 and b equals 3. So what we'll end up getting is a paraboloid that goes by the equation z equals x squared over 4 plus y squared over 9. So that means that ultimately we're going to have a paraboloid, and we're going to want it centered at the origin, and it's going to be symmetrical with respect to the z-axis, so it won't be perfect, but it'll look something like this. That's the solid that we would end up graphing. And then for part D, lastly, we can use a computer algebra system to find the surface area correct to 4 decimal places. So we can plug this in to our original equation from before, right here. We have the values of a and b. So when we plug those in, a equals 2, b equals 3, we'll plug them into our computer algebra system, and we end up getting that it's approximately 115.6596, and that would be the surface area, so that'll be units squared since it's an area.